Good morning. In Physics 1, you have learned about motion, the fundamental quantities in motion, displacement, velocity, acceleration. Then you learned about energy. Then you learned how to analyze the motion of an object using Newton's laws of motions, and after that, using energy and work concepts. Then after that, you learned about momentum and impulse. You learned about two important conservation laws, conservation of energy and conservation of momentum. You learned something about thermodynamics, heat, and sound. In the second part of the course, College Physics 2, you are going to learn about electrostatics, then electrodynamics. As the word implies, electrostatics means we are dealing with charges that are at static equilibrium. No motion is involved. Then after we learn the fundamentals of electrostatics, we proceed to electrodynamics. So now we allow charges to move. The most important thing that happens when charges move is electric current. So you have very important concepts to learn there. Then we learn about magnetism. Magnetism is associated with moving charges. Wherever there is a moving charge, there will be magnetic effects. There will be magnetism. We will learn all about that. Then we will learn about light, optics, optical instruments, and many important applications. Then we move to modern physics. In Physics 1, it was classical mechanics that you learned about. In Physics 2, you complete the picture by learning about quantum mechanics. You have classical mechanics, you have quantum mechanics. We will learn all about it. Then we apply it. We apply quantum mechanics, modern physics concepts, to study the atom and to study the nucleus. This is basically what's ahead for you in this course. By completing this course successfully, you should have enough background in physics to allow you to pass the exams like MCAT or whatever general physics exam that you may be interested in. We start with electrostatic concepts. I'd like to show you a 2-minute demonstration. That was fun. That was electrostatics. Who can explain what you have just seen to us? I'd like to give it a try. Like to give it a try? Please? No? Any volunteer to give it a try? What was going on? What made the hairs separate? I appreciate that, yeah. Yeah, like charges will repel each other. That was a simple concept. So that kid was touching a Van de Graaff generator that generates electrostatics according to the build that you saw at the beginning. By friction, it moves charges up to the upper part of the Van de Graaff, and that kid will get the charges, so the potential gets higher and higher and higher. Now, like charges repels each other. Because of that, every single hair has to repel all other hairs. Because of that, you have seen hairs trying to move as far as possible from each other. Okay? The phenomena of electrostatics is an old one. It was documented first by all the Greek scientists. They were dealing with a stone called amber. It's a precious stone. And they knew that by rubbing that amber with fur or with any piece of clothes, it will start attracting light things like hair, like dust. One common experiment that usually kids at school do is this. Okay, use a comb or any plastic, any glass, any wooden thing will do. Just rub it with a piece of cloth, with your own clothes. It will be electrified by friction, and this will allow it to attract things. We call this charging by friction. Charging by friction. In this chapter, we are going to learn all about electrostatics. We will learn what is charge, how it is related to matter, how it is related to other concepts that you are familiar with. We will learn about charges inside the atom. We will learn how to categorize materials into insulators and conductors. We will learn about the fundamental law that governs the interaction between charges. Just like in mechanics, you learn the fundamental laws for the interaction of objects based on their masses. You learned about Newton's gravitational law. Here we learn another fundamental law which is called Coulomb's law, that allow us to study the interaction between point charges. We will solve problems and learn together the strategy to solve electrostatics problems. And after that, we move from Coulomb's law into another concept, into another approach that is also used to study electrostatic through electric field. When I say electric field, the closest to you is the gravitational field that you are familiar with from physics 1. Remember free fall, gravitational field? So here you have another field, which is electric field. We will learn how to study the electric interaction between charges using the electric field concept. We will learn about electric field lines, monopoles, dipoles, multipoles. Then we will learn about few selected applications, the DNA structure and the photocopy machine. And we conclude this chapter by learning about Gauss's law. This is just a mathematical law that allows us to calculate the electric field easily. So this is the outline for this first chapter of the course. To produce electrostatics, all of you can do that. All what you need to do is just rub any object with any other object. The heat generated from friction will excite charges like electrons, and the object that has less binding energy for the electrons will lose electrons more to the other object, okay? So like here, the piece of clothes will lose electrons, and this wooden piece will gain electrons. So after rubbing this wooden piece with that cloth several times and separating them, you end up with the piece of cloth with net positive charge and the wooden piece with net negative charge. If you add both charges together, it is zero, okay? But if you keep them separated, so the piece of cloth would be positively charged and this wooden piece would be negatively charged. As simple as that. So you start with a neutral object, no charges on it. By just rubbing it, now it is electrified. Now there is net electrostatic charges there. This is another nice 15-second demo that I selected for.
Cut it out. Go.
You see the bending of the water? What do you understand from this? Is electricity a force? Right? Because the only way to attract water is to have some force acting on it. Obviously, the electricity in that rod generated force, and the force deflected the flow of water. Now, what is charge? You may find all kinds of definitions for charge. For me, I always prefer to have it simple as possible. To me, I will say charge is just an intrinsic property of matter. Wherever there is matter, there will be charges. As simple as that. What is another intrinsic property of matter that you learned in Physics 1? You remember mass? Mass, M, you remember? Mass is an intrinsic property. Wherever there is matter, there is mass. It is associated with matter. Because of that, we call it intrinsic property. It is embedded to matter. It's not gained from the outside. No. It is from within matter, mass. Okay? Mass was the central concept in Physics 1. Charge is the central concept in Physics 2 when we study electricity. Okay? So it is simply an intrinsic property of matter. Whoever created matter, he or she, we don't know, give it certain intrinsic properties. One of them is mass, another one is charge. As you proceed in your learning, you will learn other intrinsic properties. Okay? Now, there is one difference between mass and charge. Mass comes in one flavor. It is always positive. The smallest value for mass is 0. While charge, it comes in two flavors. You may have positive charge, you may have negative charge, and you may have 0 charge. Some objects will carry 0 charge. This doesn't mean that there is no charges there. No, there are charges, but the positive are equal to the negative so that the net charge is 0. So charge comes in two flavors, negative and positive, in addition to neutral or 0. There is equal amounts of positive and negative charges. Now, another point of comparison. As you learned in Physics 1, two masses will attract each other. And in Newton's law of gravitation, right, that M1, M2 divided by R squared, right? So here we have a similar law, we'll talk about it in a few minutes, which is Coulomb's law, that allow us to calculate the force between two charges. For now, we need just to understand that charges comes in two flavors, positive and negative. We need to understand that charges are conserved, just like mass. Charges are conserved. What does that mean? It means you cannot create charge from nothing. You cannot consume charge to nothing. Whatever amount of charge you started with, you will always continue with that amount. So charge is conserved. If you dig deep inside matter to investigate the source of charge, the actual source of charge is the atom, and the atom has equal amounts of positive charge at the center, which we call the nucleus, and negative charges carried by electrons that are rotating around the nucleus. The particles that are inside the nucleus, the positively charged particles, are called protons, while the negatively charged particles that are rotating here are called electrons. Typically, atoms will have equal amounts of positively charged nuclei and negatively charged electrons, and because of that, the net charge for an atom is zero, usually. If you strip one of the electrons by friction, for example, then this atom will carry a net positive charge, because now positive is more than negative. We say that this atom is ionized, in fact. Excellent. So, with this understanding of the atom and the structure of matter, now we are in a position to understand how electricity is generated by friction. So by rubbing, you generate some heat. The heat excites some electrons. The electrons escape from their mother atoms, and you end up with the piece of cloth losing electrons while the piece of wood gaining electrons. So you end up with negatively charged wood here. If you bring it closer to light pieces of paper or dust, it will attract them, as you can see. It acts with some force on them. We call this charging by friction. Charging by friction. This is another interesting thing to talk about. So, we talk about atoms as neutral entities. How about molecules, like the water molecule? This is the water molecule, H2O. You have two atoms of hydrogen and one atom of oxygen. If you completed chemistry class, you all know that oxygen has 8 protons, it has 8 electrons, and hydrogen has 1 proton and 1 electron, right? So the water molecule has 10 protons altogether, 8 inside the oxygen, 1 inside this hydrogen, and another 1 inside this hydrogen atom. 10 protons. And in addition to the 10 protons, there are 10 electrons, 8 rotating around the nucleus of oxygen, and 1 rotating about the center of this hydrogen atom, and another 1 rotating around the center of the second hydrogen atom. Now, the centers for the 10 protons and the 10 electrons are not the same point. They do not coincide on each other. There is splitting between them. Because of that, there is a net charge for the molecule, because you have 2 charges, 1 positive, 10 electrons, 1 positive 10 protons, 1 negative 10 electrons. We call this dipole. We call this dipole structure. So all water molecules have this dipole structure, which means electricity. And this explains to you when that guy in the demo used that rod that was electrified, when he brought it closer to the water attracted, okay, because of this net charge carried with every single molecule. We move on with this understanding to learn about materials. From the electric point of view, usually we categorize materials into 3 main categories. If a material allows for electricity to flow from one object to another, say this is a charged object, this is a neutral object, if you use this metal between them, then charges can flow from the charge to the neutral. Because of that, we call this nail, we call it conductor, because it conducted electricity. It conducted the charges. It allowed charges to move from the charged to the non-charged object. And at the end, you will have this symmetric distribution of charges because these two spheres are identical. So all materials that allow charges to move through freely are called conductors. Conductors. Conductors, the most common conductor that we use in household wiring is copper. Copper wires, these are the most common. But we do not stop there. All metals are conductors. Then, if you used a wooden piece, nothing will happen. No charges will move from the charged object to the neutral object. This tells us that wood is not a conductor. It does not allow electricity to flow. Because of that, we call it insulator. Insulator. It insulates. It does not allow electricity to flow. There are all kinds of materials who are insulators, not just wood. Rubber, glass, PVC, pure air, pure water. All these are insulators. They do not allow electricity to flow. The third type of materials, which is of much important excitement, is called semiconductors. Semiconductors. It has intermediate conductivity between good conductors and insulators. Semiconductors are the most important materials in our age. You see this whole computer technology around you, cell phones, satellite communications. It's all built using semiconducting materials. Okay? We will learn about semiconductors also in this course and how we use them to build very interesting and very important devices. If you allow two metals to touch each other, then charges will move from one metal to another. Because they are touching, because they are conducting, so charges will be able to move from one metal to the other. We call it charging by conduction. Charging by conduction. In other words, charges are conducted from one metal to another metal. Charging by conductions occur only when you have conductors or metals. But if you have, say, glass or wood or plastic, it doesn't work that way because charges cannot move. Charges cannot move in insulators. Okay? So charging by conduction is good when you deal with metals or with conductors in general. This is another way to charge an object. We call it by induction. The first one was charging by conduction. The second one is charging by induction. So as you can see in this illustration, you start with a neutral piece of metal connected to ground. This symbol, we call it ground. It represents earth. Earth, from the electric point of view, is just like an ocean. It has infinite amount of charges, and luckily the positive are equal to the negative charges, and because of that it's a neutral and we can work easily on it. Okay? This means if you add any amount of charge to it, or if you take any amount of charge from it, it doesn't really make a difference. Imagine yourself dealing with an ocean of equal amount of negative and positive charges. Now, if you bring a negatively charged object nearby this metallic rod, because it is negatively charged, it will attract positive charges closer and repels negative charges as far as possible. So negative charges will fly away to that ocean, to Earth, and then if you disconnect this connection with Earth, you end up with these positive charges. They will redistribute themselves, okay, because of mutual repulsions, and now you end up with a positively charged object. We call this charging by induction. Because I assume most of you, I noticed maybe 10 students signed to Clicker, so we will not use Clicker in this lecture. On Friday, we will start the lecture by reviewing what we learned through Clicker.